Welcome to the second lecture of the third week. We are going to talk about something called implicit function theorem. An implicit function theorem is a very deep idea in mathematics, used in many places, used in optimization, in differential geometry, in solutions of equations. Many aspects of mathematics is touched by this very simple idea. So, given a function say of two variables, suppose there is an equation written like this, f of x y equal to 0. Can we express y as a function of x? That is the question we ask ourselves. Once I know that there is a basically f x y equal to 0 is the z equal to f x y. So, it is a curve on the plane, two dimensional plane, and I am asking what does that curve represent? How is y related to x on that curve? For example, if I say if the equation is 2xy plus x is equal to 0, then you have x into 2y plus 1 is equal to 0, or 2y plus 1 is equal to 0, and there is no x. So, we could not represent x as a function of y here. Now, for example, if I write things like 2x plus 3y minus 6 is equal to 0, then can I represent y as a function of x? In this case, it is much more simpler, because here I can write 3y is equal to 6 minus 2x, or y is equal to 6 minus 2x by 3. So, y is represented as a function of x. This whole issue is not always possible, because for example, if I write x square into y square plus 3xy plus 2 is equal to 0. Let me try to see what I can do with it. You can say, okay, how do I take the x to the other side? Here I have y. So, if I want to take y outside, so y, you can't even do that. You can write it as some kind of product, but y would anyway remain here. So, this kind of representation is called implicit representation of a function. So, function of one variable y equal to f x is implicitly represented by an equation in two variables, implicit representation. Y is a function of x, but I do not know. How is it? Now, I do not know the exact relation. So, exact relationship between x and y is not clear to us, known to us. Suppose I say, okay, you have a situation like this, f of x y equal to 0, and you know that y must be some function of x, but you cannot find the exact relationship, then what to do? Then, but you know that the curve is very smooth and nice, suppose it is differentiable, at that every point you can draw a tangent. Can you find dy dx? So, the question is, Can you compute this? The answer surprisingly is yes. YES. The answer is yes. So, what is the tool which allows us to get that answer, and that is the chain rule that you have learned about partial differentiation. Now, basically you will think x as a function of x itself and y is also the function of x, right, and f is a function of x y. So, what you will do, you will apply the chain rule for partial derivatives. So, you compute say del f del x del f, basically you want to compute chain rule. Now, you have f, the function f x y, right. Now, you want to compute something like the derivative of f with respect to x. So, as you know in the chain rule, what you will do, the chain rule will be applied here and the chain rule will give us the following. Del f del x dx dx plus del f del y dy dx, and that is equal to 0. What have we actually done? How do we get such a chain rule? What have we actually done? The idea comes from this. The idea is that if I have a function of x y and suppose in my mind I write y as f x, so this is actually a function of x phi x, and then I am trying to find d phi dx, which is df dx. But how will I do it? So, as you have learned in the chain rule, first I have to now, okay, here there are two entries and this is a function of x and this is of y, which is also a function of x. So, what I will do, I have to first take the derivative of this with respect to the x variable, and then derivative of x with respect to the x variable, plus you know the partial derivative chain rule. Basically, it is a composition now. So, I can write this itself as a function. So, f can be written as f composed psi of x. The psi of x is a function, psi of x is a function from R1, that is R, to R2, and that is given as psi of x is equal to x and f x. That is the way to think about it, and put y in place of f x. So, del f dx dx, so del f, so you know what to do. So, you have the gradient vector into the derivative of this, right, rather sorry, not the derivative, the kind of rather the Jacobian of this. So, basically you will have del f del y into dy dx, which is same as df dx. So, once you know this and you can apply the chain rule, so phi x takes from R2 to and f is taking from R2 to R, that is it. So, you see the chain rules that we have learned and apply that chain rule, you will just get this one. So, what you do now here, dx dx is 1, so you will get del f del x plus, but this del phi, what is del f del x, because this was equal to 0, so it was 0, f x y was 0. So, it will be del f del y dy dx. So, what you finally get is dy dx is equal to del f minus of del f del x divided by del f del y. Obviously, for this to be meaningful, we must have del f del y not equal to 0. So, I have tried to explain you how can you view it and how can you apply the chain rule. This is a standard chain rule. If you have forgotten it, let me just write it again for you. Suppose you have a thing like z equal to fxy. Then for any t, you have dz dt, you have del f del x dx dt, providing x is a function of t, plus del f del y into dy dt. This is the standard chain rule. In this case, putting t is equal to x, and that would imply dz dx, but which is 0 of course in this case, because that fxy was given to be 0. So, dz dx would be equal to del f del x plus del f del y dy dt. But however, you can apply the other more general chain rules and put phi in that form, and you can try this out whether you can get this result, the same result what we are writing. So, this is the standard chain rule, that absolutely the basic chain rule, which we started with when we were studying chain rules, and I had made a complete explanation of how this comes. So, we will not get into those details right now, but this thing what we have done, this procedure of finding dy dx, this procedure. So, when we write that dy dx is minus of del f del x. Obviously, del f del x is evaluated at that point x y. All are evaluated at the point x y. I am not going to write every time that I am evaluating at the point x y. Now, I think you are now sufficiently understanding the subject to understand that we are actually computing all these things at a point. Here I am calculating dy dx at the point x. So, corresponding to that x there is a y. So, there at those x y's I am computing this del f del x basically. So, del f del y. So, when I write this way of finding the derivative, when I am not really knowing the exact link between y and x, such a thing is called implicit differentiation. An example I take from the standard text. Obviously, del f del y equal to 0 would create problems which we will get into at a later stage, but let me just get along with the subject. And for example, if I have f x y equal to 0, where f x y is given as e to the power x minus y plus x square minus y minus 1. Now, I want to find the derivative of the of y with respect to x. So, what is dy dx? Dy dx is minus of del f del x by del f del y. Now, let us try to find, maybe say find dy dx, because suppose if I put x and y equal to 0 0, suppose I am expecting the function will satisfy when I put 0 0 here, it will be satisfied, that is f(x, y) will becoming 0 0. So, dy dx at x equal to 0, y equal to 0, which means that when I put 0 and in place of x and 0 in place of y, f of x y must become 0. So, let me check. So, f of 0 0 must be equal to e to the power 0 minus 0 plus 0 minus 0 minus 1. E to the power 0 is 1. So, 1 plus 0 minus 0 minus 1 is 0. So, which means that 0 0 is on the curve y is equal to some f(x), some the curve whose function, whose nature we do not know, the exact relationship between y and x. And now, so it is absolutely logical to compute the derivative at y equal to dy dx at x equal to 0, y equal to 0. So, what is del f del x in this case? So, it is e to the power x minus y plus 2x. So, computed at 0 0, what do I get? I will get, I will put 0 0 to the power 0 plus 2 into 0. So, I will get 1. So, del f del y is minus e to the power x minus y, because of the chain rule again here, minus 1. So, del f del y evaluated at x equal to 0, y equal to 0 is minus e to the power 0 minus 1, that is minus 1 minus 1, which is minus 2. So, dy dx is equal to minus 1 divided by minus 2, which is equal to half. So, this is an example that we have computed, and this is an example through which we can show that whatever we have done is actually working. This is the way we can find out. Of course, there is a question, what would happen if del f del y or del z del y, because we have written z is equal to f x y. So, if because we have written z is equal to f x y, so you can call instead of del f del y, you can call del z del y, means writing this or this is same, is the same. Now, the important question is, what would happen if del f del y, del z del y is, suppose del z, I am in a position where del f del y or del z del y, whatever, if del z del y is equal to 0, then what happens to dy dx? Dy dx stands undefined. If then dy dx is no longer defined. So, suppose I have f x y is equal to x minus y cube. In this case, the relation between y and x is clear. In this case, I will have y is equal to cube root of x. Let us see what is del f del y. Del f del y or del z del y, whatever is the same thing, is minus 2 y, sorry, minus 3 y square. So, it implies that del f del y is equal to 0 if and only if y is equal to 0. Okay. So, but at y equal to 0, the function y equal to cube root of x, and y cube equal to x does not have a derivative. You can check it out by drawing the graph, it is not differentiable. So, y is not differentiable at x equal to 0. y equal to cube root of x is not differentiable. So, when I put y equal to 0, of course, this is y cube equal to x. So, when y is 0, x is 0. So, this is not differentiable. At x y equal to 0 0. Basically, for the single valued function at x equal to 0, this is not differentiable, and you note this. This is a standard form, standard. So, it is not differentiable even implicitly at 0 0. So, dy dx at 0 0 cannot be computed, because in reality dy dx is not, you cannot evaluate, is not differentiable at x equal to 0, since y equal to 0 implies x equal to 0. So, this is a kind of demonstration that this is meaningful only when the lower one is a non-zero stuff, dy dx. Now, we will come to implicit function theorem. Implicit function theorem tells you the following, that suppose f x y equal to 0, I am just in 2 dimension just for simplicity, but suppose we cannot write y explicitly as a function of x. We cannot write. Once we cannot write, what can we do? What it says is the following. The implicit function theorem says that if under certain conditions, if you have a point f x naught y naught x naught y naught such that f of x naught y naught is 0, then under certain conditions in a small neighborhood of that point x naught y naught, that is in a disk containing x naught y naught, is a disk in a 2 dimensional space. In a disk containing x naught y naught, you will you already know what is this ball, the disk containing x naught y naught, this circular region completely. You will around such a point, if certain condition is satisfied, you will see that y for all those x y within that neighborhood can be represented as a function of x. So, locally y can be represented as a function of x. So, under certain condition you can always write y locally as a function of x, and that is very important note. Implicit function theorem says that if f of x naught y naught is 0 and some condition, and we will see what is that condition, some condition holds at x naught y naught, you might think that this whole thing is very dry, but I will show you immediately why it is not. Then there is a neighborhood, or a set of points around x naught y naught, hood of points x y around x naught y naught, for which f of x y is equal to 0 and y can be represented as y is equal to f x. So, the implicit theorem essentially tells you this simple fact, that local representation is possible. But under what is that condition? The condition is that del f del y or del z del y at the point x naught y naught, if we evaluate that, that cannot be 0. This is the regularity condition. This is sometimes called the regularity condition. I am just writing it here, regularity condition. Absolute. Once you have this condition that this cannot be 0, then then you will have this kind of representation, and not only can be represented as y equal to fx, then you can represent dy dx as minus of del f del x by del f del y. So, the condition is del f del y evaluated at the point x naught y naught cannot be equal to 0. Then dy dx can be written as, for every such points, as minus del f del x by del f del y. At x naught y, it does not say around what are the other points, it should be. At x naught y naught it cannot be 0, but then because it is not 0 at x naught y naught, in the neighborhood it will not also be 0 basically, otherwise this cannot be computed. That is what it says, it gives you a lot more information. So, if this condition is not satisfied, then this thing may not be true around the point x naught y naught, which is lying on the curve y, which is satisfying the equation f x y equal to 0, and that is what we are going to show through an example, that this condition del f del x y, this condition that del f del y evaluated at x naught y naught equal to 0 is not equal to 0 is important. Let us see what happens if it fails. Now, consider f of x y is equal to 0 and f of x y is equal to x square plus y square minus 1. So, f x y equal to 0 implies x square plus y square is equal to 1. So, it is circle centered at the origin and having a radius of 1. Now, consider the point 1 0 or any of the points here which cuts, not these points, but these 2 points 1 0 and minus 1 0, whatever. So, take x naught equal to 1 and y naught equal to 0. So, which means I will now consider x naught y naught as 1 0, and obviously f of x naught y naught in this case is f of 1 0, which is 0. Now, take a small neighborhood, take a disk, take all the points here in this disk. Now, look at the picture, let us magnify it. This is your 1 0 point, and you have taken a disk around 1,0 point. So, when some condition holds at x naught, then there is a neighborhood of points x y around x naught y naught such that in that neighborhood there are points which satisfy f x y equal to 0 and is also the graph is also lying on the graph, that is a better way to say it, lying on the graph of a function y equal to f x, lying on the graph of y is equal to f x. So, what it says is that, so you will always find a neighborhood, and in that neighborhood you will always find some points in that neighborhood which will lie on the graph of a function y equal to f x, but also satisfy f x y equal to 0. So, you will be able to have some points on the curve, that is on the curve y equal to f x, and locally you can represent it as y equal to f x. So, a part of the graph, part of the curve can be represented as a part of the graph of some function y equal to f x. But this is, for example, here if you come, so these are lot of, let these be the neighborhood points. So, only these blue points in the part of the neighborhood, the open neighborhood if you want to say, only the blue points are the points which are lying on the graph f x y equal to 0. The blue point satisfies f of x y equal to 0 in this case. But remember, in this case for any x that I take in this neighborhood, any x y that you think is lying on the graph corresponding to this same x, corresponding to this given x here, there is more than one y, there are two y's. Actually, that is what happens, that this is the point that you have to understand, that however small you make the neighborhood, it does not matter. So, if this is your 1 0 and this is a small neighborhood you have got, does not matter how small you make. Look at this point x here and look at the corresponding y here. This x y is in this neighborhood as well as it is on the, it is satisfying f x y equal to 0 because it is on the circle, but corresponding to this x, right, drawing is not very good, that is any point here, for example here for example take this point here, any x here you see there is a symmetry, actually I am unable to draw it properly. So, here this x here, there is a corresponding y1 here and there is a corresponding y2 here, and there is a corresponding y1 here, and this y2 and y1, that is basically these points x y1 and x y2 both are lying on this curve and both are satisfying f of x y1 is 0 and f of x y2 is 0. So, corresponding to a given x there are two y's in this part. However small you make the neighborhood, it does not matter, this will always occur. So, if you take a y, you can actually have a symmetrical y corresponding to a given x. But if you come here, for example, say take any point here, far off from here on this boundary. So, you take a point like, say, point like here, a point like 1 by root 2, 1 by root 2. Then take a neighborhood, take a square this time, does not matter. You see, take any point here, y here, it corresponds to 1 x. So, any other y that you have, the corresponding symmetric y that you have does not lie in this neighborhood. Here what is happening, if you take a y1 here, you can symmetrically, because you have taken circular neighborhood, even if you take a square neighborhood, because if 1 0 is like this, if you take a neighborhood like this, square neighborhood, does not matter. So, what happens is that if you take this point here, there is another symmetrical point in that neighborhood which is also lying on the graph and corresponding to a single x, but a function, for a function, by the definition of a function, given a x there is only one y, given a x there cannot be two y, given two x's there can be a single y, but given a x there cannot be two y's. Every x corresponds to a unique y, and that is a function. Here every x here corresponds to a unique y in this neighborhood. This x corresponds to this y technically, right? This xy also satisfies the equation f x y equal to 0, but this xy point, this coordinate is not inside this neighborhood. So, when but this point 1 root 2 1 by root 2 del f del y is not equal to 0, and hence you can represent this y as a function of x. Here y will be root over 1 minus x square. So, that is the idea of the implicit function theorem, that locally there is always a chance, if del f del y is not equal to 0, local representation is possible. You can, but if del f del y equal to 0, local representation is not possible, and that's the idea of the implicit function theorem. This is a difficult theorem, it will take some time to understand, you can go through. So, the idea is that you take a neighborhood, and in that neighborhood you will find points which are lying on that curve, and also you can represent that piece of curve as a graph of a function given as y equal to some fx. Please observe this point, corresponding to this y here there is a symmetrical y here, but this xy point, this coordinates corresponding to this x, of course, this x, and there is a y here, another y dash here, but xy dash, this coordinate is not in this neighborhood around the point x0 y0, which is 1 by root 2 1 by root 2 in this case, just for an example. So, with this I end my talk. This is a slightly difficult thing, but from the next class we will go into much more mechanical thing which you can understand much more simply, and hoping that you take this course little seriously, we will get into more detailed things, but this will be extremely useful. Without an understanding of function of 2 variables or function of 3 variables, doing difficult tasks in engineering and solving engineering problems it becomes really difficult. Without mathematics, things don't advance. There is a Society of Industrial and Applied Mathematics in the US, and it is called SIAM, SIAM, and their motto is also SIAM, Science and Industry Advances with Mathematics. So, I would just request you that whatever been done here, you can look up other books, you can look up the net, you can look up other sources, just do not depend on a single source. I can be mistaken, I can have a little, maybe there are some issues where I would have conceptual failures maybe, that I have to admit, it is human to err. So, you can correct me if you want on the portal, and but it is important to go through sources, important to see applications, because in this little course of 20 hours it is not possible to do a complete justice. This is actually a course of a whole semester, and each class would be of an hour. Okay. So, good night, and actually it is night here. Thank you very much.